So I'm going to talk a little bit about just one of these methods, the simplest of them all, to give some intuition about what exactly these kinds of feature attribution based local explanation methods try to do, right? Like what is the intuition behind them? So one of the methods, and the first one in this area, is called line. And this method is actually does something very simple and intuitive. And I'm going to sort of describe a little bit about what that method is doing, and then talk a little bit about why what it is doing might work, right? So what this method does is, let's say if we were trying to explain the prediction of this point, in the sense that we want to identify what are the important input features contributing to the prediction of this point, the way this method suggests that we do that is we take that point and then we perturb that point slightly, which means we add some noise to that point and generate a bunch of different points around it. And then for all these points, we take the predictions of the underlying model whose prediction we are trying to explain in the first place. And then we fit a linear model, which is like a linear regression, for example, or a logistic regression. We fit a linear model which basically predicts the underlying model's labels on these points, right? So essentially what it is trying to do is create some sort of a local linear approximation of the underlying model, right? So that's what it is like intuitively trying to do. Okay. So just to understand why a local linear approximation of an underlying model would be a good representative of what are the features the model is using or what it is doing on that point, is because so a lot of complexity with respect to model understanding stems from the fact that these models that we use today are becoming increasingly nonlinear, right? So for example, if in this picture, let's say this light blue region represents, the negative class, and then the light pink region represents the positive class, according to the model, the way the model is creating the boundary. And as you can see, the boundary between these two classes is highly nonlinear, right? So you can see that this is like super nonlinear, which means it's going to be some sort of a combination of like several nonlinear functions that is often hard to interpret for a human end user, right? But the hypothesis or the intuition that this line paper is exploiting is that while a model can be highly nonlinear globally and therefore might be hard to explain, if you zoom in into a small local pocket of the model's decision boundary, it will behave like a linear model, right? So even if it is highly nonlinear at a high level, once you zoom in around this point, even that complex nonlinear model is, we can fit a line there and try to separate the two classes locally, right? That intuition is what this method, and in fact several other methods in this literature, are trying to exploit. And so therefore they're like, okay, I'm going to take this point, I'm going to just like add some noise to this point and create a bunch of points around this point, and then just fit a linear model on those points and the predictions being made by the underlying model. And that linear model and the weights it outputs will tell me how important each feature is to this prediction, right? So that's the logic. Yeah.
Just to clarify this figure, I think people who have a background in machine learning can directly sort of understand this space and what's happening. But am I correct in sort of explaining it to a more general audience to say, let's say we have a model that works with two features only. We plot those two features, they're X and Y, say, I don't know, patient age and patient weight, for example, or blood pressure. And then when we feed these to the model would say this is a class A, this is a class B, class A, class B, based on these points, and that's how we place these points. And the plus or circle is what class that the model sort of assigned it to. And the perturbation is to say, okay, if we have a data point like this, can we give the model data points of a similar, or let's say younger age, or we explore that space there. And that concept is then, let's say, extrapolated to models with a lot of different classes and features, but just a visual like this can be achieved by dimensionality reduction down to two.
Yeah, for sure. Yeah, I think that's pretty accurate, and that's exactly what we are looking at even here, right? So this is like one class of points, and then there's a different class of points. Yeah.